Hi friends, good evening. Hope you're with your good health. Thanks for joining again today. And as part of our HR analytics series of sessions, we are trying to see how applications of analytics can help transform the HR stream, HR domain. We looked into various things as part of our discussions, and today is another new day, and we will be talking about a new algorithm, new applications, and we'll also see how this application can help us resolve one of the trivial business case that HR people generally have trouble with. We'll understand how analytics can actually help resolve these issues, and not just this, but we will also try and understand how the specific algorithm here that we are trying to learn will help us to also give justification or explanation on what factors are influencing the outcome. As part of the data science implementation or analytics implementations in HR field, HR domain, we are basically looking into the data that is getting generated in this stream. The data can be in offline or in a specific HRMS database. But while we are trying to assess this data or access this data and try and develop some use cases, right, some solutions, one point we need to remember is that just like any other domain, we will have specific metrics to be considered. So as part of HR domain, we have a big list of metrics, and using these metrics, we will try and develop some kind of I should say applications. And we'll also try and define the results or explain the results, which will in turn help us to take appropriate decisions in the business. Now, as part of data mining, there are many things that you can actually perform using quantified or I should say mathematical and statistical models. Like we have seen survival analytics, we have seen regression model, we have seen distance-based algorithm yesterday, that is KNN model. In all these cases, we are focusing on doing predictive analytics, where we were trying to do prediction of a specific variable of interest. As I was explaining yesterday, under the data mining, we have brought two segments, and one of that is supervised learning. This approach will allow us to do the predictions of a specific variable. But in order to do this, first we need to have historical data wherein you already know what is output, right? And what are these inputs which are influencing the outcome. So there is a cause and effect relationship between these factors or features, and we are trying to establish this relationship in a mathematical form or mathematical model. That's all about your predictive analytics. We generally explain that using this equation, where y is a single column, single variable, we call it as, where capital X represents multiple variables. And f is the function which is explaining the relation between y and x. This is also known as the base equation. Now, if I talk about the traditional programming, I remember I have also spoke about this, but if I talk about traditional programming, we see that we will be given some data, but in this approach, we will have to write the logic. We define the logic and we implement that using a programming language and pass it to your machine, the computer. This will calculate and gives us the outcome, the results. This is a traditional programming approach, a typical approach. But when we talk about analytics or data mining, here we are speaking about machine learning. And when we speak about machine learning, we speak about the data. And because we'll always work with historical data, we also know what is the results, right? The outcome. So I'll have input, I'll have output, and these two will be passed to your computer. And the expectation is that the computer should help us to identify the logic which is basically defining the relationship between output and input. So computer is to figure out this logic, and this is expressed in a function form, a mathematical function form. That is this equation. Now, when we are trying to do this, there are again two broad approaches. One is the statistical approach, statistical and right, I will say mathematical based approaches, based algorithms. The advantage of these statistical and mathematics based algorithms are explainable. Okay, that means what we are trying to do can be explained. And whatever the solution that we are getting, it can be explained. Because all these are based on predefined equations, predefined logics. The other way of doing predictive analytics is black box. Though we are not discussing about black box concepts in this particular series, we will be revisiting the HR analytics modules once again. And in the next series of the sessions, we will bring in more use cases, more applications, and at that session, right, and in that series, we will also try and cover the black box approaches, which are basically the foundation for AI. The black box techniques are done in a simple way. In the previous ML programming approach, I said, right, we'll have input, plus you'll also have output. When you pass this to your computer, your machine, the expectation is the machine figures out the function, the logic. So here, how is this logic identified? How is this function identified? Or what is the relationship between these two? Is something we cannot explain. But mathematically, we will get an equation. Okay, this is the kind of equation that we get. It could be linear. But what are these weights? How X is influencing Y is something we will not be able to explain. These are called as unexplainable models. Because of this unexplainability or uninterpretability, they are called as black box model. And just to give you a gist of things, we are speaking about neural network. And this approach, neural network algorithms, are the foundation algorithms or the algorithms which are used to develop AI applications. It's all about neural networks. Okay, everything is neural networks. So we are not going into go into this black box approaches. We have seen statistical based approaches. We have talked about linear regression. Then we talked about logistic regression. These are techniques which are using the statistical approaches like y is equals to f of x kind of a relationship. We also have looked at shallow methods or shallow techniques, which is nothing but KNN approach, where we only look at the distances. And if the distances are not huge, if the two records are very close to each other, then we will be able to say that these two have similar characteristics, and hence the label can be identified for a new data. These are called as shallow methodologies. On the similar lines, we have decision trees, which we are going to discuss today. And the decision trees are rule-based algorithms. These are rule-based algorithms. So that means we are going to generate a bunch of rules, and using these rules, the decisions are made. If you see the name of the approach, decision trees, right? So we are basically speaking about a tree or a bunch of trees which allow us to take decisions. And this kind of a representation can also be called as flowchart approach. Flowcharts are used right in the same lines. We generally define the flow of various things, let's say data, and then based on the flow, we will take different decisions. On those same lines, we'll have decision tree algorithm. So what are decision trees and how do we build them? A decision tree is just like a flow diagram or a flow chart, or you can see a decision tree just like a regular tree, right? And if you talk about a regular tree, right, the tree has roots, it has branches, and at the far end, you will see leaves or fruits or flowers, whatever is your interest. Let's say leaves is more generic. So I'm going to say leaves. So each leaf that we speak about can be a decision, can be an output. And to reach to that leaf, we'll have to start at the root. So from root, we'll traverse and reach a specific leaf. Okay. So a decision tree is a tree-like structure. The algorithm that we're talking about is a tree-like structure where you have a flowchart in which the internal node represents test on an attribute. Now, this attribute is nothing but a variable in our data set, a feature in our data set, or one of the fields you can see. And when you're taking the test, the results that we are going to get are nothing but the branches. And each branch is representing the outcome of the test, right? That's what it means. When we are doing a test, you'll get outcome. That outcome is nothing but the branch. And when we keep doing this, we end at a leaf node. That's the end point, right? So each leaf node then can be categorized into one of the output categories, one of the output columns. We will see how this decision tree can be grown. But yeah, a path from root to leaf is represented as a classification rule. We'll have to traverse from root to leaf node. So if you see, a decision tree contains three types of nodes: a root node, a branch node, and a leaf node. Okay. A root node, branch node, and a leaf node. This is how your tree looks like. The three types of nodes that we talked about, we spoke about. This is where you'll have root node. Then we have internal nodes. And finally, this is your leaf node, or it is your terminal. Everything starts here at the root. Okay, and then we keep branching out until we reach the leaf node or terminal node. So a decision tree has to be grown. And when you're growing, these are the questions that we look at, especially these two. The first one talks about how you grow the tree, all right? What strategy are you going to apply to grow the tree? In short, which variable in your data set would you choose to keep at each node? So can we quantify this a question, right? What will be the value of each split? We can also measure that. Then the second question is, when do I stop it? Should I keep growing the tree until I have everything covered up? Or can I stop it? Right, when I say can I stop it, I'm saying can I take a decision with respect to the output variable, and I don't have to extend the tree branches to the last leaf, right, individually. That's the question. In short, when should I stop? And another point, will I be able to assign the leaf node or the terminal node to an output category? This is also something that we'll have to look at. It has to be mapped to the output label. These are some of the things that we'll have to look at. And when we ask the first question, these are the points that you need to remember to address the first question, which is how do you define or how do you grow the tree? What variable should you use to split the branches and grow the tree? The approach that we are taking is called as a greedy algorithm approach. It's a very simple approach. We keep constructing the decision tree. We grow the decision tree by splitting the data into branches. Right, so tree is constructed in a top-down recursive divide and conquer manner. So you're reversing the tree. Generally, root will be at the bottom, but here we are talking about root at the top and leaf at the bottom of the branches. So tree is constructed in a top-down recursive divide and conquer manner. At start, all the training examples are at the root. Right, to start with, if I have 100 records, let's assume this case, okay, I have 100 records, 100 employees database, and this is, let's say, 10 columns. To start with, our data set, right, is completely considered, okay, and this is your output variable y. And if I take a very simple example, will the employee resign or not? It's a binary case, assume. This is the discussion. The decision can be taken because of various reasons. Okay, those reasons will be your input factors, but your output is binary. Now, to start with, everything is at this stage only. Okay. Now, one of the factors we will take, x1, x2, x3, so on and so forth. Let's take gender, employees' gender. When you talk about employees' gender, we may have male, female. So I will split this data based on this one column. So your 100 records are getting split. Maybe I have, let's say, 60 records and 40 records, or vice versa. It could be anything. Not balanced. I just wanted to show that this is not balanced. So either way, 40-60 or 60-40. So I get balanced, response, remaining response records here, 60 records and 40 records respectively. So if you look at this, at the beginning of your decision tree, first branch, you have 100 records. But as we go down the branches, the number of records is reducing. Right? At each branch, the number of records obviously will reduce. So to start with, all the training examples are considered at the root, and then we will keep splitting the data into branches and grow the tree. Now, what if I have a branch which is like, let's say, salary? Salary is one of the column, right? What if this comes into the picture here? Because salary could have a very, very wide range of options. That salary could be very, very wide options. If you talk about the gender, you have probably only two branches, right? Two options or two branches. But what if you have something like salary, which can be any value? We don't know. We call these data as continuous data, salary data as continuous data, because you have almost infinite possible options there. We can go to any decimal levels, right? So we don't know. So many different options are. Now, in these kind of cases, I cannot grow those many branches. A tree cannot have infinite branches, for example, right? So in these kind of scenarios where your data has a very, very wide range, we call them as continuous data, right? We generally convert this into discrete fixed set of options. For example, salary can be level 1 salary, level 2 salary, level 3 salary, or you can put any levels that you wish. Right? At a socioeconomic status level, we can say high salary employee, mid level, and low level. So this way we can discretize the data for branching out the details. Right? So that is your categorical data. So you're always having fixed set of branches. Your output, your input should have fixed set of options. And then we'll try to split the data using a statistical measure called entropy and information gain. There are other ways, other cases also, other algorithms also, but we'll look at this one specific case which says information gain. And once we decide how to grow the tree, we will start growing the tree, but you also need to know when to stop it. So what are the conditions for stopping the partition? Ultimately, we are doing this approach to decide on an outcome, right? If I can do that, if I can take a decision with respect to the output, then that means I'm able to, I mean, we can stop the growth of the tree because you're able to take a decision. You don't need to further grow the tree. That's the logic. Now, this can happen in three different options, three different scenarios. All samples for a given node belong to the same class. Right? Samples means records. When you're splitting the data into branches, the records that we are getting could have same class. If that is the case, then you're able to take a decision. Right? You don't need to further grow it. There are no remaining attributes for further partitioning. This is majority voting. There are no remaining attributes means you don't have a column, you have a single column. And here you go with majority to take a decision with respect to your final outcome. That means you have a single column where you're basically having the decision to be made, whether the employee is going to resign or not. Let's say I have 5 records. Out of that, 3 records says employee, right? 3 different employees are saying that they will resign. 2 employees are saying they will not resign. So we go with the majority rule where we say the chance of these employees resigning is more. Hence, we will decide that that branch will give us the factors of resigning. Okay, then there are no samples also left for comparison. You have a single record, single employee details. Now, this is a historical data. If a single employee is there, you know what is that employee status is, whether he is still working or resigned. Right. So this way, there are three different options where you can take a decision. I'll talk about the simple example here. You can imagine this with respect to your employee resigning or not resigning. We have age of the employee. Now, age is a continuous value. It can have any range, right? It has a large range. Probably it can start somewhere around 20 to 23 to 60, 65 as well, right? And age can be in decimals also. So too many options are available. So we are grouping this data into three segments. We're saying anything which is less than or equal to 30 is one group. Right? A bunch of people who belong to 31 to 40 is one group, and greater than 40 is another group. Okay, so this way we are splitting the data. So age is becoming now 3-level branches. It can have 3 options. Or we call these options as levels. Here income also has 3 levels. Students have 2 levels. Credit rating has 2. And whether the employee will resign or not. In this case, we are looking at another example where computer is being purchased or not is given. So your output variable is also 2. So this is about your sample data. Now let us try and take a decision when a new person is walking in. Okay, assume a new person is walking in. You might want to upfront know what would be the output for that particular person. Here we are talking about a customer, whether the customer is going to purchase the computer or not. And if I talk about HR related thing, the example that we are discussing, will that employee is going to resign or not? When is he going to resign? He or she is going to resign is something which survival analytics module will tell. Right? That algorithm will speak about when. But here we are talking about yes or no, whether the person will resign or not. So using this data, we'll have to construct the decision tree. So I'm taking student as one of the node, and this is your root node because we're starting the growth of the tree here. So this student example becomes the root node example. And then we are going to further split these branches. Now we keep branching out until we can decide on stopping the growth of the tree. And we've already discussed that it can happen when there are no records. There is only one record. So this is one of the areas where you can immediately stop the growth of the tree. There's no record further to grow the tree, right? That's one way. No columns, only one column is there. Even in this case, we will be able to stop the growth of the tree. But here, as you can see, we have multiple columns. So none of the branch has single column, so no problem. Next, we have low. The income group is low. This basically speaks about the age, credit rating, and class, right? So we have different options here. Again, here we are splitting the data into income. This branch also, high and medium are there. Now I cannot stop growing the tree in this case, or in this case, or in this case. This is because we don't have an option to take a decision. Decision is talking about, will I be able to predict the label or not? In this case, I can say, yes, the customer will be purchasing the computer. Same way, though I have two records here and two columns, both the rows you can see belong to the same class. Right? All the samples belong to the same class. Even then, in this case, I will be able to take a decision. Right? In this case, we will be able to take a decision. Right? So student, we have income, high and medium. In these two cases, the customers are going to purchase the computer. So you can say the employees are going to resign for two different factors. This is a rule that we have constructed here. We have successfully created a set of rules. If the incoming customer is a student, and if that student falls under an income group of either high or medium, then we have the decision to be conducted. Here we say both the cases, the customer is going to purchase the computer. Now here I will not be able to take a decision because there is variation in the class variable. Right? All the three branches you can see, there is variation. Some cases they say yes, some cases they say no. So uncertainty is there, right? So in this case, we cannot take a decision. So we further split it. So when I further split it, the branches, some of the branches are giving me a case where we will be able to take a decision. Again, whenever you have multiple records and each of these records is belonging to a different class, then you will not be able to bring the right decision here. So we keep splitting it until we take the decision. So here we can see that there are 11 different rules. All of them start at student as the rule. Apart from root node to the leaf node is one classification rule, and we have 11 rules here. Right? So when a decision needs to be taken, we have 11 different options to consider. Next, if I try and take a different approach, a decision tree can be grown like this also, where I take income as the root node, not the student this time. When I keep doing that, I grow the tree like this. Right? So we get 10 rules here. So in the previous case, we are getting 11 rules. If I alter my approach, I get 10 rules. Now, among these two, which one is better? That's a question that we need to look at. In order to address this question, imagine you are the store owner where you are basically selling the computers, or you take an example of your employees. You are working on whether the employee is going to resign or not, kind of a case. You might want to do a prediction upfront. So you're developing a model on that. Now, to take a decision, you'll have to go through 11 different options or 10 different options to take a decision. Which one do you think will be better? 11 different options means you need to take more time in coming up with the final decision. So on a single employee, a new employee is joining, right? Or you're considering another new employee to assess. So to conclude that this new employee is going to stay back or resign, we are going to verify 11 different rules or 10 different rules. Which option is better? Right? In other words, if I have to put it, do you need a mango tree, mango season, right? So I'll talk about mango trees here. Do you want a mango tree, which is like a very big banyan tree, which gives us fruits, or you're interested in a very small 2 feet tree or 4 feet tree, which gives you a lot of fruits, hybrid tree? Which one do you prefer? This is a simple question which can address the question that we are trying to resolve here. Always, I mean, it's obvious, right? Always we need quick results, right? We are eager to find results. If I have 11 rules, then obviously it's going to take more time compared to 10 rules. Now, these two trees that we have grown are manually, right, developed, and we have different options that we have chosen. Now, why should I choose income as the root node? Why should I choose age here? Why not probably, right, credit rating in this branch? Why should I use age, right? So these kind of questions is definitely something that we need to ask ourselves, and we can see that these right combinations that we are developing should actually help us to take decision as quickly as possible. So we need to try and get as right least number of rules as possible, and for doing that we use entropy. Entropy is a measure which captures the variation in the data, or you can say uncertainty in the data. Variation or uncertainty. Measure of disorder or impurity, or uncertainty or variations. More variations you see in the data, like 50% of cases are there. If I have 100 customers, I'm saying 50 customers have purchased the purchased the computer, 50 customers have not purchased the computer. Or if I talk about 100 employees, and out of historical, okay, out of these 100 employees, 50 employees have resigned, 50 employees have stayed back, then in this case you'll not be able to talk about the entropy much. Here we have highest impurity, right? We need pure regions. Pure regions means everything either should be yes or everything should be no. That is pure regions. We don't want mix and match. Okay. Now what we do here is we use this calculation called entropy. We do a measure. There's a formula for it. We'll discuss that. I'll show you that in the next slide. And we have to calculate entropy on the entire data set. We call this E of B. If I have 100 data, right, 100 records or 100 employees data, on this entire database, we have to capture the entropy. Entropy is nothing but the variation in your output, this column. And then to identify the best tree, which gives us the least number of rules, we will take one of the attributes here and split the data set. Right? To start with experiment, example 1 or experiment 1. Take X1. And using this X1, you split this tree into branches. Maybe you'll have 3 branches. Once you split the data into 3 branches, you will again calculate entropy after the split. So maybe entropy 1, entropy 2, entropy 3. Entropy after is nothing but summation of entropy 1, entropy 2 plus entropy 3. Now for decision making, you can see that if I can approach the branches, I mean, if I can get a branch which has same records, right, or same values in the final column, then we basically will be able to take decisions faster. We will get less number of votes. So we are trying to get homogeneity. Homogeneity means a similarity here, right? Then we'll also take, let's say, X2. Let's say here I'm taking another variable, x2, example 2. So first case, data set 1, attribute 1, split and see what is the entropy. Similarly for sample 2, record 2 or observation 2, my bad. Here you have the field. You take that as the variable of attribute to be splitting. Then let's say it gives us branches. Now, when you talk about these branches, let us assume that everything says yes in E1 and everything says no in E2. This is nothing but your homogeneity. There is no impure regions. So entropy in this case will become 0 if you don't have mix match. If you have pure regions, then you have entropy as 0. Entropy is uncertainty or variation, and we are saying it is 0 in this case. So this becomes your ideal attribute to decide on the split of your data at that level. Right? Now, here we have a calculation called information gain, which is nothing but the difference between entropy on your entire data set, which we call it as entropy before, minus entropy after E of A. This gives us the information gain, and higher the information gain, better the partition, because E of B before the partition, whatever the entropy is, that will remain constant. But after you split the data on an attribute, it could be any attribute. We do the comparison for all the attributes. The attribute which gives us the best homogeneity, that means this value will be least. If this is least, then the difference will be more, right? So higher the information gain, better the model, or better the partition. Okay, so that is basically what information gain is. Ultimately, we are trying to find out the most homogeneous branches in your decision tree. The formula to look at this is given here. This is a calculation. Let me talk about the formula here. Entropy is calculated as minus P of I log base to P of I summation. For example, if you look at this case, I have 1, 2, 3, 4, 5 cases, right, of no cases. So out of how many? 40. So probability of no is 5 by 14. If probability of no is 5 by 14, probability of yes will be the remaining data points, which is nothing but 9 by 14. So P of I is the probability of the category given in this data set, and we have got this result. So I will say probability of minus 5 by 14 or minus 9 by 14, whatever is feasible. We write that minus 9 by 14 log base to 9 by 14. When you do the calculation, you get entropy as 0.94. This is entropy. Now, after the split, this is before the split on the entire data set we do, but after the split, if I take age here, the age is categorized into 3 branches. Less than or equal to 30, 31 to 40, and greater than 40. We have already seen. So we will get 3 branches, right? If I use age to split the tree, I get 3 branches. Less than or equal to 30, 31 to 40, and greater than 40. So what is the entropy in this data set? What is the entropy in this data set? What is the entropy in this data set has to be captured. And when you look at less than or equal to 30, you have 5 observations which specifically fall under this group. All right. So out of that, if you actually work on this particular 5 records data set, you will say minus 2/3 log base to 2/3 minus, sorry, 3/5, my bad, minus 3/5 log base to 3/5. That's your calculation of entropy on age being less than or equal to 30 case. Now, when you talk about 31 to 40, 1, 2, 3, 4, right? 4 records are there, and you can see all the 4 records belong to yes class only. So there is no variation. This is pure region case. So we will get minus 4/4 log base to 4/4 minus 0/4 into 0. This is minus log base to 1, and log 1 is equal to 0. So we can clearly see that the entropy here is 0. Right? Entropy is given as 0. Similarly, we do it for the remaining data points, and we get this calculation. Now, what we are doing is we are capturing the entropies that we have calculated here, the proportion, right? For example, 5 records are there here in this data set, and the entropy is so much. For 4 records, the entropy is this. For 5 records, again, for right out of 14, this is the entropy. So when you write this formula, you will get the calculation as 0.694. Now, when you do the calculation of entropy before, this is entropy before, this is entropy after, we will do the difference between these two and get the information gained for age column, because we are using age to make the partition. The same logic will be implemented for income, where income is also giving 3 groups. So same logic will be implemented for income also. Then student as well. Student, you have 2 branches. Yes, no. Credit rating also fair or excellent, 2 branches. So this way we keep splitting this and we get different information gains for each of the column. And if you see, this is the information gain calculations, and 0.246 is the highest value, which is given when you are splitting the data using age. That means age is giving us the maximum homogeneity in right, partitioning the total data set. Hence, what we use, we take age as the attribute to make the partitioning, because this is the first step. This becomes your root node. So I get 3 branches. Now repeat the entire logic on these 3 branches. This is anyways, decision is taken. No variation, so decision is taken. Right? So this is your final tree. You will get 5 branches. So is the customer student, age less than or equal to 30? If yes, whether that person is a student or not. If he is a student, only then the person is purchasing, otherwise the person is not purchasing. But if the age is between 31 to 40, then I know for sure the customer is going to purchase the computer. That means you can say, I mean, if I have to put it in the HR perspective, the use case that we are discussing, example use case, where we are trying to identify whether an employee is going to resign or not, then you have 5 different rules which can help us understand that a given particular employee will resign or won't resign. So if the age is less than or equal to 30, and if the student, right, it does not fall under student, then definitely we can say that the computer is or the person is going to resign. If the age group is between 31 to 40, then for sure that employee is going to resign. And if the age is greater than 40, then what are the financial commitments? You can say very high or average. Then based on that, you're going to take a decision on whether to move the organization or not. Okay, so these are the kind of rules that we can generate with respect to the decision tree. Okay. The algorithm is called as greedy approach, friends, and it gives us the rules like this, classification rules. That's what we call them. In this particular decision tree, we have 5 rules. Right, so that is your decision tree model. Now we also have a variance in decision trees. We call them as ensemble techniques. We talk about ensemble techniques. And in ensemble techniques, we generally have combination of many trees. You can see here, we have only one tree. But when you talk about ensemble models, we'll have multiple trees which can be used. Right? Combination of many trees. All right? This combination of many trees is called as, we have different approaches, but one of the approach that we can talk about is random forest. The name of the approach is called as random forest. In this random forest, we will take subsamples of the data, and on each subsample, we'll apply a decision tree. Sample 1, decision tree on sample 2, decision tree on, right, decision tree 3 on sample 3, so on and so forth. And each of these decision trees will be trained on this subsample data, and then new data will be passed to the algorithms so that it can do the prediction. Right? Each model is going to now do the prediction. So when you talk about this prediction, new data case, each of this decision tree is going to give us different result. Maybe, possibly each decision tree might give you a different result because of the partial training it gets. Now, once we do this partial prediction, these weak learners are going to give us some result. We'll take all these results and then we aggregate them. Right, so we are aggregating the tree. And this aggregated tree results will tell us the final outcome. Okay, final output. This is one such example of ensemble techniques, friends. There are other techniques also. We basically use a very popular terminology called bagging and boosting. These are approaches. One of the examples of bagging is random forest. One algorithm under this bagging is random forest. We also have something called a stacking, voting, right? Tree-based and non-tree-based algorithms. But these are the tree-based algorithms that you can blindly use for decision tree models. All right. So, friends, as we have seen, there are many ways to actually try and build solutions on data, right? So ML workflow is basically implemented on given data. And these ML algorithms are going to help us churn the data and define insights. Give results. Using those results, you will take the insights from the data. That's a simple approach. that we can talk about in right, analytics space. But we are specifically saying that the business cases that we are dealing with is in HR domain. If you are coming from HR background, then you can take the examples here that we discussed and then try and build various algorithms, right? Descriptive and predictive algorithms, and use those predictive analytics to, or descriptive analytics to, make an appropriate decision. Right, so that's your HR domain example. And we can solve a lot of different problems in the industry, especially with the metrics that we were trying to capture. These are the metrics that we need to look at. Only some examples. We're not talking about everything here, of course. Time to hire, cost per hire, early turnover, time since last promotion, revenue per employee, performance and potentials, billable hours of employee, cost of HR per employee, turnover, engagement rating. So various other metrics are also there, which we need to capture and assess those metrics to bring in analytical approach to take decisions. Right, so this is basically what I wanted to convey as part of our HR analytics sessions. Hope you have enjoyed, hope you have understood the applications of analytics in HR domain, and you probably have got to know some use cases also, which you might want to implement. If you need any help while you are trying to implement these algorithms on your business area, when your work area, do not hesitate. You can always approach us and we will guide you to proceed further and take the advantage of all these skills that we have learned in the past 1 week or 1.5 weeks, I should say. And ensure that you refer to the Tame the Python sessions. We are starting the mandatory programming language Python sessions for free from 11th of July. Right? I would recommend, or I would suggest everyone to take the advantage of these free sessions. These are mandatory sessions. Assume that these are mandatory for everyone. Slowly you can pick up things, but taking the first step is important. So do ensure that you take that first step towards the most happening space in the industry, that is analytics space. And the starting point would be your first step towards practicing Python, especially if you're coming from a non-programming background. And you will see that Python is absolutely fun to deal with. And it's not like your programming languages that we generally get scared of, the Javas, the C programs and all that. Okay, so do not hesitate. Python programming is just like English. You attend the sessions, assume it is mandatory, and you will enjoy the programming language, and that would eventually help you to transform your careers into more happening space and better and bulky salaries for you. So good luck, and I would see you again around. Stay in touch. Do not hesitate to contact us if you have any queries. Thank you so much, everyone, and take care, friends.